Okay. Right. So good day, everyone. So today we're going to proceed with lecture 5. So lecture 5 is basically going to start on a new chapter. Yeah, a new chapter. So for today's lecture, we are going to have a look at the attenuation in optical fiber. So basically, the main topics, the main title for chapter 3 is a transmission characteristics in optical fiber. Okay. So this is a continuation, I can say, from what we have learned from previous chapter 2. Okay, so chapter 2 we have learned about the light propagation in optical fiber. So the topics or the theories that we have learned in chapter 2 will be usable, yeah, will be very useful in understanding, in learning chapter 3. Yeah, because those chapters are interrelated, yeah. Okay, so let's have a look at the content for today's lecture. So these are the things. So if you can refer to this, the bottom content of this slide, this is the excerpt from the course information. Yeah, so for course information is very simple. It just state the main topics in chapter 3, which include the attenuation, the absorption, scattering, dispersion, and fiber bending loss. Okay, so basically, chapter 3, in terms of the content, it is quite, big. Yeah, content is quite big. A lot of concept, a lot of things need to be understood from chapter 3. Okay, and for today's lecture, basically the attenuation comprise of these topics, absorption, scattering, and fiber bending loss. So that's why we have a content for today's lecture. We'll be discussing about the factors of attenuation. So I put here there should be three main factors. Number one is the absorption of material. Number two is the scattering, and number three is the bending loss. Okay, so dispersion is another topics, which is also things to be learned. Is very important, and the scope is quite wide. It's quite big. That's why if you can refer to the files or to the slides that I have been uploaded yesterday, we have two parts for dispersion topics. Yeah, so part one will be discussed tomorrow, inshallah, and the rest will be discussed next week. So a lot of things need to be understood in terms of the concept. Yeah, it's very important. Okay, so just to let you know that we are going to have a test one. Yeah, test one. So this week it will be the 4th week. So my plan is to have a test one on a week 7. Yeah, on a week 7. So it will be around 2 weeks from now. Week 4 is this week, so that's next week will be week 6, week 5, week 6, and week 7. Okay, so week 7 is a week before the break. Yeah, the break is on week 8. So my intention is to have a test one on the week 7, and the content for test 1 will be on chapter 2 and chapter 3. Yeah, chapter 2 and chapter 3. So which include the chapter that we have learned previously on light propagation in optical fiber, and also this chapter. Yeah, this chapter on the transmission characteristics of optical fiber. Okay, so please take note on test 1. Don't worry on the formulation. All the formulations, all the formulas will be given. You don't have to memorize. Right? Okay, and the thing is that you're doing the test online, right? So online, I think you can refer to any books. So that's the benefit of having an online test. So it's okay, never mind. So let's proceed with this lecture 5. So we're going to have a look at this introduction. Yeah, that should be the first topic today, and followed by absorption, scattering, and bending. Yeah. Okay. Okay, so this is about attenuation. I believe that you have learned about the attenuation in PCOM. yeah, before. So you have been taught about the concept of attenuation. The concept is the same, yeah, concept is the same, but the difference is only on the medium. So previously the medium is general, but for this lecture the medium is based on fiber optics. Yeah, so we're going to refer to optical fiber attenuation. Okay, so by definition, attenuation is defined to be this. It's a logarithmic relationship between the optical input power and the optical output power. Okay, so we know that attenuation is a measure of a signal strength, a decay of signal strength. Okay, I believe that you have understand this very well, yeah. And in mathematics, it shall be then formulated based on this equation here, where the alpha is a symbol for attenuation. It will be 10 log, yeah, power in, the power which is transmitted at the source, yeah, transmitted at the source before the input to the fiber, and power out is the output which is measured at the end of the fiber. Okay, so we have 10 log power in or power out, and going to have divided by z. Z is the length, yeah. Z is the length of the distance, yeah, it's the distance from the input. Okay, so in general, in optical fiber communication, the alpha is written or measured to be in the units of dB per kilometer. Okay, so that should be the units for the alpha, the fiber attenuations, right? dB per kilometer. Okay, so if we refer to this graph here, so this is an examples of relationship, yeah, between the output power and the distance z. The vertical axis is your output power, and the horizontal axis is the distance z, the measured distance. Okay, and we can see the effect when we have three values of alpha. Okay, so we have in here, for example, I give you three values of alpha. We have alpha of 0.1, alpha of 0.3, and alpha of 0.5. So we can say that as the alpha value is higher, okay, we note that the value of output power is very small. Yeah, let's say for instance, if we take a distance of z of 5 kilometers here, you can see that the value of alpha, which is higher, resulted in a small value of output power as compared to the alpha of 0.1. Yeah, which shows that as the alpha is increased, the output power will also reduce. Okay, so that's the relationship, yeah, between just to show the impact of these equations here, related to the output power and also the distance of z. Yeah. Okay, hopefully you understand about these issues here. Okay, so we are now ready to discuss about the factors or the contributors of the attenuation. So in optical fiber, there are three main factors. The first one is what we call as absorption. Yeah, the alpha, which is due to the material absorption. Okay. Number two is the alpha due to the light scattering in optical fiber. And number three is the alpha attenuation, which is due to the bending, yeah, fiber bending. And I believe that for those who have entered the lab, optical lab in third year, third year, second semester, last semester, I believe, yeah, last semester. Oh yeah, last semester we have I believe that maybe some of you managed to enter the lab in the very early weeks, yeah, maybe 3 or 4 weeks earlier. I mean, the first 3 or 4 weeks time before we have a PKP, the MCO, and I hope that you gain something. All these very short terms, yeah, 3 or 4 weeks time. Okay, and I believe that you did some experiment on this light transmission in terms of attenuation measurement. Okay, on how you measure the loss of the optical fiber, on the bending effect. Yeah, so I believe that some of you have done the experiment, yeah, on these topics of attenuation. So I believe that the idea is still there. You still have the idea on this effect of bending, effect of scattering or absorption, to the attenuation, yeah, of the optical fiber. But the difference is that what you did in the lab is basically use the plastic fiber, yeah, the polymer based fiber, the black colored fiber, which is having a very high loss, yeah, as compared to commercially used fiber optics for communication. which is silica base. Yeah. So silica base is having very small value. It's about 0.2, 0.1 or 0.2 dB per kilometer, as compared to polymer base, which is higher. Yeah. So, but I believe that that should be some sort like a exposure to the students on the fiber optics communication. It's good actually. Yeah. Okay. So now let's proceed now with these factors: absorption, scattering, and bending. So if you have any questions, you can just stop me anytime. Yeah, within the lecture time. Okay. Okay. This is attenuation. So what we have here, the figure here shows the effect of attenuation. Yeah, just to make it clear on this effect of attenuation. So for instance, we have these pulses, yeah, pulses transmitted at the input. Yeah, I mean this is from the input source which has been modulated. Yeah. Sorry, someone is trying to get in the class. I would have to admit. Okay. Right, we'll go back to this discussion here on this attenuation. Okay, so this is the output of the modulator, yeah, which is going to the input of the fiber. So this is the fiber optics, the cable, and this is the output. So in attenuation, we can see that there should be a difference on the amplitude, yeah, difference on the amplitude. For instance, we compare the input signal, the amplitude, and the amplitude after at the output side. So we can see a difference in terms of the amplitude value. So the difference in the amplitude of the signal is the effect of attenuation. Yeah, so attenuation will then affect the level, yeah, the level of the signal transmitted throughout the fiber. Okay, so that should be the effect of attenuation. Okay. All right. So out of these three factors that we have discussed in the previous slide, we can further divide these factors into intrinsic factors and also extrinsic factors. Yeah, intrinsic is something that cannot be controlled. Yeah, it's happening inside the fiber optic itself, yeah, inside the structure itself. While the extrinsic is something that can be controlled. Yeah, can be controlled. Okay, the intrinsic, for instance, is the absorption of the material. So it depends on the material used. Yeah, so this is something that cannot be controlled. Yeah, because some of the material do portray good performance at certain wavelength and not that good performance at certain wavelength. So this is the behavior of the material, which is something that cannot be controlled, and we have to adapt to this behavior. Okay, and then we also have a scattering. Yeah, scattering is also something that cannot be controlled because when we fabricate the fiber, it involves a lot of, I can say, particle formations. Yeah, particle formations in the fiber optic, a small particle formation in, let's say, for example, bubble, ions. Yeah, so all of these cannot be controlled. Yeah, because it happens naturally in the material itself. So these particular particles, the ions, all of these will give rise to the effect of scattering. Yeah, will give rise to the effect of scattering. So that will be discussed later in this slide. Yeah, but just to let you know that these two things, absorption and scattering, are the factors that cannot be controlled, and it exists naturally. Yeah, naturally due to the material behavior. Okay, so that's intrinsic factors. Okay, for the extrinsic factors, which is actually due to the fabrication, the factory, yeah, the factory, the setup of the fabrication, the environment, yeah. So and also the macro and macro bending. Macro and macro bending is something that actually caused by human factors. Okay, so we categorize these under the extrinsic factors. Okay then. All right, so hopefully you understand about these issues of attenuations, effect of attenuations. Okay, so let's have a look at the first factors, which is material absorption. Okay, so we can say that absorption is a mechanism, loss mechanism, which is actually related to the material composition, okay, the material factors, and also the fabrication process. Okay, so in terms of metal absorption, we can divide it further into two factors. Yeah, the first one is the material composition, material natural behavior, and then also related to the fabrication process of the fiber. And then this is classified into two types here. The first one is at intrinsic absorption. Okay, so it is based on the metal components. And the second one is the extrinsic absorption, which is due to impurities. Yeah, impurities introduced. So these impurities introduced is actually exists during the fabrication. Yeah, during the fabrication. So during fabrication, we have a lot of impurities. Yeah, which cannot be controlled. Although we did it, we try to do it in a very clean environment. Still, yeah, still you're going to have impurities produced in the fiber optics. Yeah, so natural. Yeah, we cannot get 100% perfect, clean or perfect fiber optics. Yeah, some things, some impurities still there in the structure. Okay, okay, right. So the effect on this absorption is that the optical energy, which is transmitted in the fiber optics, this energy will be absorbed, by these impurities, by the effect of material components, and once absorbed, it will be then dissipated as a heat. So heat dissipation means that it's a loss. Yeah? When we have a heat dissipation, so it's a loss. Same like what we have in a circuit. Yeah, in the electrical circuit, we have a resistor. Yeah, in the resistor, the energy, the electrical current will be converted into heat, so it's a loss. Yeah, so it seems like same things happen here in absorption of light in fiber optics. It will be dissipated in the form of heat, and it will incur a loss. Yeah, and further on is attenuation. Yeah. Okay, so I state here that intrinsic absorption is a natural property of the glass or silica. So SiO2 is a glass symbol, a chemical symbol or chemical notation for a silica, SiO2. Okay, and the effect of this glass absorption is very strong in the UV region. Okay, so we have learned about the light region. You have the UV, you have the visible light, we have the infrared region. So all of these have been learned in lecture 1 and 2. So if you cannot recall this, so my advice is please go back to that lecture 1 and 2 to understand what is the region for the UV, what is the region for the visible, and what is the region for the infrared later on. Yeah. Okay, so back to this discussion. So the effect of this glass absorption is very strong in the UV region, okay, which is for the wavelength value of less than 400 nanometer, and also for the infrared region, IR region, which is having a wavelength of bigger than 2000 nanometer. Okay, so this is the region where we have a very strong absorption effect of glass. So that is why in a commercial application of fiber optics, we never have a transmission of light in this region, which is below than 400 nanometer and bigger than 2000 nanometer due to this effect of strong absorption. Yeah, because a strong absorption will result in very high loss and very high attenuation, which is not practical for fiber optics communication. So this is why our communication, our wavelength of interest for communication, for fiber optic communication, is between 400 and 2000 nanometer. Okay, so that's the reason, yeah? So selection of wavelength is very important. If you wrongly select the wavelength, so the loss will be very high, yeah, and attenuation is very high, and it's not practical to operate at that particular wavelength. Okay, so hopefully you understand. Okay, two major mechanisms for this absorption in glass. Number one is fundamental UV absorption H. Okay, so this is due to electron transition within the glass molecule. Okay, so this is more towards physics, so I'm not of interest to discuss further on this. Yeah, transition, not transition. So if you're interested, please have a read on your own. Yeah, but the effect is due to this. Yeah, electron transition within the glass molecules at the UV range. Yeah, which is below than 400 nanometer. And for the IR absorption, which is bigger than 2000 nanometer, this absorption loss, I mean the loss is due to this molecular vibration, yeah, which is the molecule of Si and O, okay, silicon and oxygen molecule. We have a vibration, so this vibration will incur heat, will produce heat, yeah. So that's why the loss is very high at the IR region, bigger than 2000 nanometer, yeah. Okay, so this is a diagram, a figure which shows the loss. Yeah, so in the vertical axis here we have a loss. Yeah, we have a loss of value, and for this horizontal axis is the energy, the photon energy. Okay, which shows basically this diagram shows the loss. Yeah, the loss that incur with respect to the wavelength. Yeah, with respect to the wavelength. So you have a wavelength axis on the top here. Okay, down here is the photon energy, and at the top axis here we have a wavelength. Okay, which shows that the blue this line here, dotted lines, is the UV absorption. Yeah, it's a UV absorption line. Okay, which justify that if we are dealing with the wavelength which is less than 400 nanometer, okay, this is 500 nanometer, and this is 400 nanometer, we are going to have a very high loss. Yeah, a very high loss for a wavelength of 400 nanometer and below. Okay, and this line shows the UV absorption effect. Yeah, UV absorption effect. Okay, while this line here, okay, a dotted line but labeled with the red color here, is the line which shows the loss value for the infrared region. Yeah, infrared region, and it shows that as the wavelength increase, yeah, as the wavelength increase, you can see that 2 micrometer or 2000 nanometer here, the loss is very high. So this is a infrared region. Okay, right, and we can see that if we operate the wavelength higher than 2000 nanometer, yeah. So the loss due to absorption of material, absorption of glass will be very high. So our interest is just within 0.5 and also less than 2, 0.5 and less than 2. So this is the region of interest that will be a region of interest to operate, yeah, to be operated in the fiber optics communication. And further on, we have here the scattering loss. Okay, supposedly this is scattering should be discussed later on, but never mind. Yeah, we have to discuss also based on this diagram. Okay, we have the scattering loss will then will then give effect at different wavelength. Okay, you can see that interestingly, this scattering diagram and this absorption diagram, all of them will actually converge into a very small loss in between 1 and 1.6, around that, around 1 and 1.6. Yeah, you can see from this diagram clearly. So all of these will converge to a very small value, around 1 and 1.6. And there is also a graph which shows the loss due to hydroxyl ion, the OH negative. Okay, this is due to the water. Yeah, water ion, OH negative. So when we have water component in a glass, so it will incur loss, and this loss is due to hydroxyl ion. Yeah, hydroxyl ion. So we're going to discuss later on. Yeah, but for this particular graph, it shows that the hydroxyl ion will be having a peak at this value. Yeah, so we have This is the graph which shows the line of OH absorption value, and it has a peak at this value is around what? 1.25, around that. Yeah, 1.25, around that. And interestingly, we have a bottom peak. Yeah, we have a bottom peak at these 2 points here, around 1.5 and around 1.3, something like that. So that is why in a commercial optical communication system, our wavelength of interest will be at these 2 wavelengths. Yeah, which is at 1.3 and 1.5 later on. But this is early informations, which is due to this diagram. But the idea of showing this diagram is to show the effect of glass absorption at the UV level, UV region, and also the infrared region. Okay, so hopefully you understand the effect of glass absorption for different wavelengths. Yeah. Okay, but this graph is very useful. Yeah, it's a standard graph used in showing the effect of absorption, effect of scattering for different wavelength values. Yeah. Okay, let's proceed. Okay, this is a discussion about the X-ray absorption. Okay, this is what I meant just now. So this X-ray absorption, which is due to this fabrication, will actually caused by the absorption. Yeah, absorption due to the water ions, OH ion or hydroxyl ions, and it is produced during the fiber fabrication. To be exact, during the fiber pulling process by the oxyhydrogen flame. Okay, so during this process, there should be a water trap in the fiber structure, and this will give rise to the hydroxyl ions, and further on, it will produce the absorption loss, yeah, due to these formations of hydroxyl ions. Okay, so these hydroxyl ions are bonded. Okay, it's bonded in the glass structure, and as what we have seen before, and also here, also the same diagram as before. Yeah, so if you can allow me to refer to the previous slide. Okay, this line which shows the OH absorption peak basically is similar to this one. Yeah, similar to this one. The line, the solid line is the same. Yeah, it's the same. Which shows that the peak of absorption for hydroxyl ion is around 1.39 micrometer. So this is the peak of hydroxyl ion, around 1.39. I put here is 1,400 nanometer. It's the same. It's similar to this. Yeah? So that's why we cannot operate at this peak or at this wavelength because of this effect of hydroxyl absorption. Okay. So due to this, by relating these issues of hydroxyl absorption at 1,400 nanometer, and the effect of this absorption and scattering line of loss, then we come out with a understanding or agreement that the spectral windows exist around 1.3 micrometer and 1.5 micrometer basically are unaffected by this OH absorption. So we can view from this diagram that we can have a it's a bottom, yeah, it's a bottom peak of the hydroxyl absorption, which is at 1.3 micrometer. This is known to be a second window, and there should be a bottom peak also, which is lower than before, which is a third window, and this happens at 1.55 micrometer. Okay, that is why our interest is to work at this particular wavelength. Yeah, which is at 1.3 and 1.55 due to this effect, which are number 1, very small absorption, number 2, very small scattering, and number 3, very small hydroxyl absorption loss. Okay, so that's the reason why in modern communication system, the interest is to work at these 2 wavelength values, 1.3 and 1.55, but more interest are towards, is towards 1.55 micrometer because the loss is smaller. Yeah, the loss is about 0.2 dB per kilometer as compared to other wavelength. Okay, so hopefully by now you understand why we work at 1.55 micrometer of wavelength due to this principle of trying to reduce the loss due to absorption, the glass absorption, due to the scattering of the fiber, yeah, and also due to the effect of hydroxyl absorption loss. Okay, hopefully you understand. And I put it here that the impurities, which can also produce during the fabrication process of the fiber optics, such as the ferrum ion and also copper ion, yeah, it has a effect on the absorption of light near the infrared region, and the loss can be as high as 1 dB per kilometer. Okay, so that's why in fabrication process of fiber optics, we try to reduce these unwanted impurities because it will incur higher losses to the structure of fiber optics. Okay, hopefully you understand, yeah, all these effects of absorptions. Okay, somebody's trying to get in the class. Let me. Okay, nobody. Okay, never mind. Let's proceed. Okay then, so these are the things that we have concluded based on the previous slides. So basically there are 3 windows, yeah, if I can refer back to the previous slide. There are 3 windows here. Okay, we have 3 windows. Windows number 1, first window, which is at 850 nanometer. Yeah, this is the windows that have been used previously. Yeah. Also, we have a second window and a third window. So these windows that basically are related to the wavelength. So I put it here that the first window, which is at 850 nanometer, attenuation is quite high, 4 dB per kilometer. And then we have a second window, which is at 1300 nanometer, attenuation of this value, 0.5 dB per kilometer. And for the third window, which is of current interest, at 1550 nanometer, attenuation is very small, which is 0.2 dB per kilometer. Yeah. Okay, so this is a standard wavelength used in today's communication. Yeah, today's optical communication wavelength. Okay, so this is a C band. So normally for 1550 nanometer, it is categorized or classified under C band. Yeah, C band. Right. So we have S band, L band, U band, but our interest is on C band. Yeah, 1550 nanometer. Okay, hopefully you understand clearly on the absorption or metal absorption. Any question on absorption so far?
So far, no, Doctor.
So far, no, Doctor.
Okay, hopefully you understand it clearly. Yeah, very good. Hopefully. Okay, now let's have a look at the second factors, which is a scattering. Scattering. Okay, so what we have here is a diagram which shows the effect of scattering. Okay, so noted that there is a small bubble there, a green circle, a 1, 2, 3, 4, 5, 6. Okay, this is what we call as inhomogeneities or impurities. Yeah, inhomogeneities and impurities. And this is something that exists naturally in a glass material. Yeah, in a glass material. Okay, so in terms of a definition, scattering is defined to be a change of direction of light rays. Somebody is trying to get in the class. It's 10:40 already. Why so late? Yeah. Okay. Right. It's defined to be a change of direction of the light rays or the photons after striking a small particle. So we have this a small particle. So when the light striking these particles, the effect will be the light rays will change its direction. And the effect will be somehow there should be a probability that the modes of light propagation will be changed. Yeah. Okay, we have learned, I believe, that there are few type of modes in the fiber optics. We have the guiding modes, which is the mode which is actually guided in the core. We also have a leaky modes. We also have a radiation modes. Yeah. So all of this leaky and radiation mode is the modes which is said to be propagated not in the core but in the cladding. Yeah, the leaky and radiation mode is the mode that is actually propagated in the cladding due to the effect of this light which is initially propagating in the core, but somehow it will then propagated in that cladding due to some effect, which include the effect of scattering. Okay, so if we can base on this diagram, this is a ray of light, a modes, yeah, a modes. Okay, we can see that this light do obey the critical angle definition, in which we have learned in chapter 2 that for the light to fully propagate in the fiber optics core, it must obey the total internal refraction, in which the angle of incidence must always bigger than the critical angle. Theta c is the critical angle. So we have learned this initially, yeah? Okay, but somehow throughout the propagation, yeah, it will then strike this particle, and as a result, might be or probably the ray of light will change its direction, and somehow the ray of light will be then having an angle of incidence which is smaller than theta c. Okay, so when the angle of incidence is smaller than theta c, the light, which is initially a guiding mode, will be then freely propagated in the cladding, which will produce the leaky mode. So this will cause, or this will incur loss. And this loss is what we call as the scattering loss. Okay, yeah? So this is the principle which need to be understood when we want to discuss about the scattering effect. Yeah. Okay. So the scattering can be further categorized into two types. So I put it here. We have what we call as a linear scattering, and we also have a non-linear. Yeah, linear scattering and non-linear scattering. So we are going to discuss what is meant by linear scattering and what is meant by non-linear scattering. Okay, so for a linear scattering, I put it here that it is a mechanism which causes the transfer of the optical power within one propagating mode into a different mode. Okay, so this is what we have discussed from the previous diagram, yeah, in which the power initially in the guiding mode, which is the mode propagating in the optical fiber core, will be then transferred into a leaky mode. So leaky mode is not in the core, but it's a cladding, so it will incur loss. Yeah, right. So this is, I said here that they will involve a transfer of power. Yeah, transfer of power. So by right from here we know that due to this leaking, yeah, or I can say transfer of power, the effect will be the amount of power propagating in the core will be reduced. Yeah, so this will incur a scattering loss further. Okay, so I put it here also. So you need to understand that leaky or radiation mode will then propagate or radiated in the cladding. Okay, so this will effect on the attenuation of light. Okay, and linear scattering by right is due to two main causes. The first one is refractive index fluctuations. Okay, what is meant by refractive index fluctuations? Okay, so imagine that in a core, okay, we know that for a glass, the index is about 1.45 something, yeah, 1.45 something. Okay, somehow, we know that we cannot get 100% pure material. So somehow there should be a changes in the value. For instance, I refer back to the previous slide, yeah, sorry. Okay, if you refer to this slide, might be if I consider the point here, yeah, that I shown by my mouse here, okay, this point here might be the index will be 1.4553, for example, yeah, for example, 1.4553, but maybe at this particular point, the index is different, maybe 1.4511. Okay, you can see that. So this is what we call as inhomogeneities. Yeah, inhomogeneities, where the index is not uniform, it's not homogeneous. So this is normal in a real world scenario. We cannot find 100% homogeneous material. Yeah, we cannot find 100% homogeneous material. Somehow there should be some inhomogeneities produced. So these inhomogeneities due to refractive index changes or refractive index fluctuations in the core will incur scattering. Okay, hopefully you understand. The effect of refractive index changes will also give effect to this what we call as a linear scattering. Yeah, and also related to it, we have a density and compositional variation, which is related to the structure. Yeah, to the structure, or I can say a molecular structure of the material. Yeah, so it's interrelated between the refractive index fluctuations and density and compositional variations. Yeah, okay. So basically, we can have two types of scattering, yeah, which is categorized under linear scattering. The first one is a Rayleigh scattering, yeah, which is named under Mr. Rayleigh. Okay, and also we have a Mie scattering. So normally when we discuss about linear scattering, we need to discuss about these two, Rayleigh and also Mie scattering. So what is meant by this Rayleigh and Mie scattering? So let's have a look on these two. Okay, the first one, Rayleigh scattering, is said that 90% of total attenuation is attributed by Rayleigh scattering. Okay, see, 90% of total attenuation is attributed by Rayleigh scattering. So allow me to refer back to the diagram that we have discussed previously. Okay, and I'm going back to the slides. Yeah, sorry. Okay, we notice the line here. Notice this line, yeah. Okay, this is scattering loss. Sorry, this is scattering loss, and from what we have learned before, this scattering loss, major effect of this scattering loss is due to Rayleigh scattering. Yeah, major effect of this scattering loss is due to Rayleigh scattering. So what is Rayleigh scattering? Okay, the state is that, the Rayleigh scattering state that it is resulted from inhomogeneities that exist in a form of refractive index fluctuations. Okay, so which means that in fiber optics, refractive index fluctuations, I've mentioned before, is something that cannot be controlled. So it is a major contributor to the scattering in fiber optics. Okay, so it shows here, yeah, it shows here that this is your inhomogeneities. Let's say, for example, fluctuations of refractive index. So when the light propagates in it, the light will be scattered. Yeah, it will be scattered, and as a result, it will then radiated as a leaky mode or radiation mode, yeah, radiated modes. Okay. So it stated that Rayleigh scattering is severely affected when the wavelengths of operations are short, yeah, or I can say short as compared to the size of the structure in the glass. Okay, so the effect will be very critical if the size of these impurities, yeah, is somehow almost similar to the wavelength of operations. Yeah, so the longer wavelength will be less affected. So this is a physics of Rayleigh scattering. So to understand this further, you can refer to this physics literature on discussion on Rayleigh scattering. But in terms of the equation that relates the coefficient of Rayleigh scattering, this is the one, yeah, which shows that Rayleigh scattering coefficient, yeah, this is the one, is actually depending on the N, and it stands for this refractive index of the medium, the P, which is photoelastic coefficient, the beta C, which is compressibility of TF, I'm not sure about this, sorry, and also the Boltzmann constant, and also the temperature. And it is inversely proportional to the lambda, which is agreed with this discussion just now, which shows that as the lambda is higher, the coefficient will be smaller. Yeah, which shows that if we are having a longer wavelength, the coefficient will be very small, and as a result, the scattering effect will be smaller. Okay, so this will be the equation that relates the coefficients of Rayleigh scattering. Don't worry about this equation. Just show you the effect of the coefficients, the factors that affect the coefficients. You don't have to memorize this, yeah? And no questions will come from this equation, don't worry. I just want to show the effect of this coefficient of Rayleigh. What is the effect of the Rayleigh scattering, basically? Yeah, so we know that the main effect will be on the wavelength, also on the refractive index values, yeah? But there should be some equations that can be used in approximating the Rayleigh scattering loss in dB per kilometer, and it's given by this equation 1.7 multiplied with 0.85 over the lambda to the power of 4. Okay, this equation maybe will be used, yeah, maybe will be used, but this will be given to you. You don't have to memorize, yeah. So note that all the equations that are important will be given to you. Never memorize the equation. The important thing I want you to do for this subject is you have to understand the concept of fiber optics communication very well. Okay, right. So any questions so far on this scattering? No?
No.
Okay, good. All right, so I mentioned to you just now, so this is the diagram that give you the Rayleigh scattering effect, yeah? So this is the one which shows that Rayleigh scattering is inversely proportional to the lambda power of 4 based on this equation, yeah? Based on this equation, it shows that the Rayleigh scattering is inversely proportional to the lambda power of 4, and it shows that as the lambda increase, the scattering will also reduce, yeah? Okay, you got the point there, yeah? And then we have a Mean scattering. So allow me to finish this before we end the class today. Yeah? So the Mean scattering is another type of linear scattering in which the scattering effect is due to larger particle size. Okay. So previously for the Rayleigh scattering, it is due to smaller particle size, but for the Mean scattering, it is a scattering effect which is due to larger particle size, and I put here is more than 0.1 lambda. Okay, so these are the inhomogeneities that is actually resulted resulted in Mean scattering, which are actually the fiber imperfections, yeah, fiber imperfections in general. So we have number one is irregularities in the core cladding interface. Yeah, so we know that at the core cladding interface, yeah, we know that the light will be having a total internal reflections at that particular boundary or interface between the core and the clad. So somehow this irregularities, it means that we have a structure. I can say a corrugation. Corrugation. Corrugation is somehow like a roughness. I can say a roughness. Surface roughness. Surface roughness that exists between a boundary of the core and the clad, because we are having different material, yeah, different material. The core, although both are glass, but the index are different, so the composition of the core and clad will be different, yeah. So due to this, there should be a corrugation or surface roughness due to these interfaces, yeah, due to this interface. So this corrugation or this roughness or impurities at this interface or core and cladding, the size is higher. The size is big. The size is bigger. The size is bigger as compared to the size of homogeneities due to refractive index fluctuation, as what we have learned in Rayleigh scattering before. So these fluctuations, I mean the roughness at the core and cladding interface, which is bigger in size, basically will result in the Mean scattering, because when the light propagate or when the light strike these impurities or this corrugation structure, or I can say roughness structure, yeah, the light will be scattered. Yeah, the light will be scattered, and as a result, the loss will be incurred. Yeah, due to this what we call as a Mean scattering. Okay, so the same things apply here. The core cladding refractive index difference along the fiber length. So this is the 1 and 2 basically are interrelated. Yeah, core cladding interface, irregularities or the surface roughness, and also related to the refractive index different. Yeah, because of different material used. Yeah, and number 3 is a fluctuation, the strains and bubbles in the fiber optics. So I did mention in the earliest part of this lecture, in your fiber fabrication, we have formations of bubble, formations of strains, yeah, in the core, and the size of this bubble and strain are quite big, and when light strike these bubbles or strain, it will incur a scattering, and this scattering effect is under a category of Mean scattering. Okay, right. So I'm going to stop here on the Mean scattering. I thought I can finish this lecture 5 by today, but it seems that we cannot finish it. and because a lot of concept need to be explained to you. Hopefully you understand this in a very clear picture, yeah, on the scattering and absorption so far. So inshallah, we're going to proceed tomorrow on this non-linear scattering by tomorrow, and we're going to have few examples before we proceed with lecture 6 part 1 on the dispersion or intermodal dispersion tomorrow morning, yeah. Okay, that's all for today. If there is any question, you can ask me now before we end the class. Any questions so far?
No, Doctor.
No, yeah? Okay, good. For your information, I did record this video, I mean this lecture, because from my WhatsApp message last week, few of your friends did mention that they face difficulties in internet connection. So to help these students, I record these lectures and going to post it in my YouTube channel. So feel free to view the lectures for the sake of revision, yeah, and hopefully it will help you. But for the previous lectures, chapter 2 and chapter 1, I'm sorry, I forgot to record it. So hopefully from this lecture onwards, going to record it and you can gain something from it, yeah. Okay, guys, since there is no questions, I'm going to sign off now. Thank you very much. I'm going to post one more time the slide, the QR code for attendance, please. For those who have not slide the code, scan the code, please do it so. Yeah, thank you very much, guys. Hope to see you again tomorrow morning at 9 o'clock. Yeah.
Thank you, Doctor.
Thank you very much. Assalamualaikum.
you.
Bye-bye.
Thank you, Doctor.
Thank you.